equivalent circuits of the PN junction diode. We have seen what is about the PN junction diode and the current equation regarding the PN junction diode we have seen. Now, what are the equivalent circuits of the PN junction diode? When you want to analyze the circuit which is involving the PN junction diode, it is required to replace the diode with small electrical circuits. Okay. So, but we have two types of the biasing for the PN junction diode. Already we have seen about this one. This is the PN junction diode circuit symbol, and this side we can tell it is a P side, and right side terminal is the N side. We can able to bias this one in two ways. So I can give forward bias using like this, and I can give reverse bias by providing the battery like this. That means lower voltage we have to provide at the N side compared to P side. So simply with one battery, if you want to provide the forward bias, the positive terminal of the battery should be given to P side, and negative terminal of the battery should be given to N side. Then we can tell the diode is under forward bias. But it is not the only way of providing the forward bias. In our previous class already I have told about all these things. You should able to provide the voltage at the P side must be greater than voltage at the N side. This can be achieved not only by using a single battery. This can be achieved by using two batteries also. And this can be achieved by providing here 0 volts also. Or this can be achieved by providing this side 0 volts also. Or this can be achieved by providing the negative voltages also. But the condition is the P side voltage must be greater than the N side voltage. That is enough to tell the diode is under forward bias. Same thing you can able to apply here also. Here we should maintain the Vp must be less than Vn. Then we can tell the diode is under reverse bias. So here forward bias, here reverse bias. So now our topic is about getting the equivalent circuits of the PN junction diode in forward bias and in reverse bias. So in forward bias, already we have seen the characteristics of the PN junction diode. So if you take voltage on the x-axis and current on the y-axis, then we'll get the exponential characteristics for the diode. Like this we'll get. So in the initial level, even though you are providing the forward bias voltage from 0 to certain voltage, here current has not been increased. Current is 0, even you are providing certain positive voltages. But once you are getting this voltage in the forward bias, then only current starts to rise in the exponential manner. Okay. So this nature we have to include in the equivalent circuit also. How it is possible? How it is possible means simply you have to provide this voltage, that is actually we have seen the cut-in voltage or the threshold voltage represented with VTH or V gamma. Okay. Once you have provided this much amount of voltage, then only current starts to rise. Below of that voltage, current is equal to 0. After that, this is the portion. Otherwise, you've been able to see this entire forward bias characteristics into two parts. One is the first part where current is equal to 0, second part where current is available. Okay, here current is available in the exponential manner, here current is equal to 0. This is what we are seeing. So current is equal to 0, and that means here infinite amount of resistance is there. But here current is available. That means here finite amount of resistance is there. So whatever the curve is there here with non-zero current, that can be represented with a certain resistance value. Okay, because it is in forward bias, I am representing that one with the forward resistance RF. Then we need to provide this much amount of voltage, then only it is possible. Can I take the resistance value, finite amount of resistance value for entire forward bias characteristics? No. This entire curve is representing the forward bias characteristics only, but this finite amount of resistance is available for the part of the forward bias characteristics where current is equal to non-zero. That means from here to here only, this resistance RF can be suitable. But when you take here current is 0, here infinite amount of resistance is there. So once you have to cross that particular V gamma, then only RF is suitable. So by understanding all these things from the graph, now I can able to provide equivalent circuit for the diode which is in forward bias. Okay, what is that? I need to cross this V gamma. Once I cross the V gamma, then I can able to take this RF, resistance RF. So this is the equivalent circuit for the diode. Okay, which is in forward bias. It is the equivalent circuit of the PN junction diode, which is in forward bias. And in forward bias, already we know that current is in milliamps. That means it is a more amount of current only. So that if current is more, resistance is less. So this RF is around 100 ohms, 120 ohms like that. It is simply 100 ohms like that you can able to take. And V gamma is based on the type of the material which is used to manufacture the PN junction diode. Based upon the silicon material, based upon the germanium material, it will be decided. Like 0.6 for the silicon, 0.3 for the germanium you can able to take. Okay. So these things you have to provide. So this is nothing but the equivalent circuit of the PN junction diode which is in forward bias. Now coming to reverse bias case. In reverse bias, whatever the little amount of current we are getting, that current is due to minority charge carriers. Otherwise, vice versa we can tell, because the current in the reverse bias is due to minority charge carriers, the current is very, very low. Okay. So in the forward bias, the current is in the order of the milliamps, but here the current is in the order of microamps or nanoamps. Very, very small amount of current is there. Okay. So what we need to represent now, in order to mention this, so simply we will take a large amount of resistor. Here also you will take resistance only. Here also we'll take the resistance. That resistance I am representing with RR, reverse resistance, because the diode is in the reverse bias, but this resistance is in the order of the mega ohms, 10 power 6, very large value. Why? Because there is no current. If current is completely zero, I can say this RR is infinity. But current is not completely zero. Little amount of current is there. That is in the order of the microamps or nanoamps, that is due to minority charge carriers. Okay. So very little amount of current is there, that is due to minority. So current is there. That means the resistance value must be available. Okay. So current is very, very low. That's why resistance is very, very large. Now we got two things. When the diode is in the forward bias, we can replace that one with a series connection of one voltage battery whose value is equal to cut-in voltage of the diode, and that is in series with one small resistance that is around 100 ohms. But when you take the diode is in the reverse bias, we can replace the diode with only one resistor, but that value should be very, very high. Okay. So here summary I will take, when you have the diode in PN junction diode in forward bias, then it can be replaced by, it is equivalent to the circuit of series connection of V gamma and one small resistor RF, like this we get. Okay. Now another one, when the diode is in reverse bias, then I can replace this one with a resistor RR which is in mega ohms. Okay, these are the equivalent circuits of the practical PN junction diode. Okay, practical PN junction diode means we can able to replace based upon the biasing technique which is provided to the diode, we can replace the circuits like this. Okay, then now ideal diode we will see. Ideal diode is not existing in practice. For understanding purpose, we will take this one. Okay, first point is not existing in practice. Not existing in practice. Okay. So if you take diode symbol is like this only, then I am taking now the equivalent circuit of the practical PN junction diode first. For explanation purpose, I am taking this one. When the diode is under forward bias, this is equivalent circuit we have taken just now. And when the diode is in reverse bias, I need to take only one resistor which is very large value of mega ohms when the diode is under reverse bias. These circuits are valid for practical PN junction diode. But whenever it is becoming the ideal, when you take the ideal PN junction diode, what will happen? When you take the ideal PN junction diode, there is no question of the depletion region. So when you start the forward bias, immediately current will start to rise. That means if you see characteristics of the ideal diode with respect to the characteristics of the practical PN junction diode, you can able to understand this one. So practically, the PN junction diode characteristics are like this. Okay, V I, this is the forward bias, this is the reverse bias. And if you see ideal diode VI characteristics, then how you will get in the sense, it is in the forward bias one straight line we will get, vertical line we will get. And in the reverse bias one horizontal line we will get. So this is representing simply forward bias and this is representing simply reverse bias. You see, you no need to wait for certain voltage to get the rise in the current. Immediately, it will get the large amount of current only. So here, V gamma is equal to 0. And current you see, it is very large. Okay. So it's a slope. If you calculate the slope, what will you get? Slope is equal to y2 minus y1 by x2 minus x1. That means y variables are currents and x variables are voltages. So if you take the inverse of slope, 1 by slope, you will get V2 minus V1 by I2 minus I1. It is the resistance only. So resistance can be obtained by taking the inverse of the slope. Okay, whatever it may be, for the forward bias, it is the vertical line. Vertical line means slope is how much? Infinity. So 1 by infinity means 0. That means for this part, you will get resistance is equal to 0. And what about this one? It is a horizontal line. So slope is equal to 0. It is having slope is equal to 0. So 1 by slope is equal to, you will get infinity. That means here resistance is equal to infinity. So only two things are there. Anyhow, V gamma is 0. Why V gamma is 0? We are no need to apply certain amount of voltage. We no need to wait for the cut-in voltage to get the rise in the current. You see, immediately it is getting the rise in the current. So there is no question of the V gamma. So V gamma is directly we can take 0. So V gamma is 0, RF is 0 in the forward bias characteristics of the ideal diode. What about this one? In the reverse bias characteristics of this ideal diode, no minority charge carriers flow. So current is always 0 in the reverse bias. So this is what we'll get. So if you apply these things in the practical diode case, you will get ideal diode equivalent circuits. You see what will happen. So V gamma is equal to 0 I am making, RF is equal to 0 I am making, voltage is 0 in the short circuit and resistance is also 0 in the short circuit. So simply you can take one short circuit when the diode is under forward bias, it is ideal diode. So when the ideal diode is under the forward bias, so simply what is the equivalent circuit? Short circuit. When the practical diode is in forward bias, the equivalent circuit is the series connection of V gamma and RF. But if you take the ideal diode, the equivalent circuit will be simply a short circuit. Diode should be replaced by a short circuit. So at this moment, we can tell it is working like a on switch. It is working like a on switch. Now coming to reverse bias. Here practical PN junction diode, when it is under reverse bias, we can replace with a large amount of resistance RR. That RR is in the order of the mega ohms. This is the information we know about that. Now already we have understood that when we come into the ideal diode case, the reverse resistance is very large. Reverse resistance is infinity because current is 0. So reverse resistance is infinity. That means it is nothing but open circuit. Okay, you see how it is there. If you consider the ideal diode and if you keep in forward bias, the equivalent circuit is a short circuit. When you keep the ideal diode in the reverse bias, the equivalent circuit is the open circuit. Open circuit is nothing but off switch. So when you keep on switching the ideal PN junction diode in between forward bias and reverse bias, though that is working like a short circuit and open circuit. Short circuit, open circuit, like this it will be working. So that we can tell PN junction diode is working like a switch. Okay. If it is only working like a on switch, we cannot tell the PN junction diode is working like a switch. There should be two operations. One time the current has to flow, that is called on switch. Second time current should be equal to 0, that is called off switch. Then only we can tell the PN junction diode is working like a switch. So that the application of the PN junction diode is the switch. The application of the PN junction diode is the switch. Equivalent circuits, all the things we can write at one place. So in forward bias, if you take ideal case, this is the equivalent circuit. Here V gamma we can take and then RF we can take. And then if you keep the diode in the reverse bias, the diode can be replaced by a large amount of resistance, that is RR. It is about practical diode. And if you take the ideal diode, These two are becoming zero, simply short circuit. Short circuit is the equivalent circuit of the ideal PN junction diode. And when you take reverse bias, the diode can be replaced by open circuit. So these are the ideal diode equivalent circuits, and these are the practical PN junction diode equivalent circuits. Now we will enter into the another topic called rectifiers. Okay. So rectifier is actually for the converting the AC pure AC signal into pulsating DC signal. Rectifier is actually the electronic circuit. Rectifier is electronic circuit which can convert pure AC signal into pulsating DC signal. In the next slide, we will see in detail about what is pure AC signal and what is pulsating DC signal. Just here I am giving the definition of the rectifier. Rectifier is a circuit, electronic circuit, because that is involving the electronic device like diode. Using the diodes, we can able to perform the rectification operation. Okay. So here what is pure AC signal, what is the pulsating DC signal, those things we are going to see. One thing you have to remember, rectifier will convert the pure AC signal into pulsating DC signal only. Rectifier cannot convert to pure AC signal into pure DC signal. That is what you have to remember. Pure DC we cannot get as the output of the rectifier. You take any type of the rectifier. Okay, we have 3 types in our syllabus. So you take any one of the 3, you will not get a pure DC signal as the output of the rectifier. Remember that point. So rectifier is nothing but pure AC to pulsating DC only. The main important component of the rectifier is the diode. Because of the diode only, this operation can be possible. Remaining components may be available, but the rectification process can be done using the diode only. Using the diode only. Okay. Now, why do we go for the rectifier means most of the electronic equipments will be working with a DC. But available thing is pure AC signal. So that pure AC signal is to be converted into pure DC. That can be done by this power supply. Pure AC should be converted into pure DC. This is what you will see in the power supply. But it is not a single block. Okay, in the power supply we have several blocks. Out of all the blocks which are available in the power supply, one of the blocks is nothing but rectifier. And that is the first block we can able to tell. So here I will take the block diagram of the power supply. So the first block of the power supply is nothing but rectifier only, and our topic is the rectifier. We will focus on this one. After the rectification process, the output of the rectifier should be given as input to the filter. And then from the filter, the output whatever we are getting, that should be given to regulator. These are the blocks available in the block diagram of the power supply. Okay. So power supply will take pure AC signal. Already here I have given. So here pure AC signal you will provide. The output of the rectifier is nothing but not pure DC signal. As I said earlier, pure AC signal can be converted into pulsating DC signal. The output of the rectifier is nothing but pulsating DC only. That pulsating DC should be given to filter as the input. So what is the filter input is nothing but pulsating DC. The filter output will be fluctuating DC. Here also we will not get complete DC. Fluctuating DC will get. Okay. So this fluctuating DC signal will get at the output of the filter. Fluctuating DC signal will get. And this fluctuating DC signal will give as the input to the regulator. Here we will get pure DC signal. Here we will get pure DC signal. Here we will get pure DC. Okay. So pure AC will be converted into pure DC by using all these blocks. Okay. Our concept is about rectifier. Now one by one we will see. What is pure AC signal? This pure AC signal is the input for the power supply. Because the first block of the power supply is nothing but rectifier, the input for the rectifier is also pure AC signal. So we need to know about this one. Finally, we should get pure DC. We need to know about this one. The output of the rectifier is nothing but pulsating DC. We need to know about this one. And the fluctuating DC is the output of the filter. Okay. So now, what is pure AC signal? pure AC signal means you can take sine signal or cosine signal. Any one you can able to take. So here for the explanation purpose, I am taking the sinusoidal signal like this. So here the signal is changing with respect to alpha. Because it is a sine function, we can tell during the first half cycle it is positive, during the second half cycle it is negative, and the cycles will be repeated like this. Okay, it is a pure AC signal. What are the characteristics of this pure AC signal is nothing but, you see, for half of the cycle, it is positive values are available. For next half of the cycle, it is having the negative half cycle. So that is why it is called a bidirectional signal. Sometimes it is having the positive values, sometimes it is having the negative values. So that we can tell it is a bidirectional signal. Okay, pure AC signal is called a bidirectional signal. Another characteristics of this one is nothing but its average value is equal to 0. You can use the formula to calculate the average value. Average value can also be called as DC value, or it can also be called as a mean value, that is equal to 1 by t integral 0 to t. For example, this signal is x of t signal. That x of t signal is to be integrated over one period. You no need to take here 0 to t only. You can take from any t naught to t naught plus t. That means over one period we are performing the integration. So mean value is equal to 1 by t integral t naught to t plus t naught x of t dt. You need to integrate the signal over one period and divide it with the time period. Then whatever the value you are getting, that is called DC value. This DC value or the average value is equal to 0 for the pure AC signal. And one more thing is no harmonics. No harmonics. Harmonics is nothing but what? N into F naught or N into omega naught. Omega naught is the fundamental frequency. F naught is also fundamental frequency, but F naught is measured in hertz and omega naught is measured in radians per second. So what is N into F naught? It is the integer multiples of the fundamental frequency. F naught is the fundamental frequency, that is 1 into F naught. When you take N is equal to 1, that is representing the fundamental frequency. When you take N is equal to 2 times of the fundamental frequency, N is equal to 3 times of the fundamental frequency. So integer multiples of the fundamental frequency is called harmonics. Okay, but those harmonics are not available in the pure AC signal. These are the characteristics of the pure AC signal. Here 3 characteristics I have given. So pure AC signal is a bidirectional signal because that can contain positive values for some time, negative values for some time. Next, pure AC signal, DC value is equal to 0 or average value is equal to 0. And for the pure AC signal, no harmonic. Okay, that means only fundamental frequency will be available. Integer multiples of the fundamental frequency will not be available. Then we can tell that one particular signal is called pure AC signal. Now coming to pure DC signal. Pure DC signal I can give in 2 ways. So pure DC signal means it is one of the example, and another example for the pure DC signal is like this. Below the x-axis I am taking here. For example, it is plus 2 volts, it is minus 2 volts. Like this I can give. So DC signal can be positive, DC signal can be negative. If you take only this one, it is only one side. Okay, for all values of alpha, always it is having the positive values only. So only one type of the voltage it is having. That's why it is a unidirectional. It is another example. In this example also it is having only negative values. Negative and positive are not available. Negative and positive are not available. So that I can tell pure DC signal is a unidirectional signal. It is unidirectional signal and its average value is equal to its value directly plus 2 volts. And in this case, average value is equal to minus 2 volts. Like this we can able to tell. No fluctuations. Straight away it is constant value, either plus 2 volts or minus 2 volts we can able to take. Okay. Then we will coming into this pulsating DC signal. Pulsating DC signal is important for us because the rectifier output is pulsating DC signal only. And we are going to see 2 types of the pulsating DC signals. One is like this, it is extending, and another pulsating DC signal is like this, it is continuing like this. Okay. So here 2 types of the pulsating DC signals you are seeing. By seeing these 2, you can give the definition of this one. What is the definition we can give? Is it a bidirectional signal or unidirectional signal? It is unidirectional only because this is containing only positive values. It is also containing only positive value. So we can tell pulsating DC signal, one of the property is unidirectional, and its average value is not equal to 0. For the pure AC signal, average value is equal to 0, but here average value is not equal to 0. Okay, and then it is containing the harmonics. Harmonics are available. N into F naught is available. Okay, that means if you take F naught, it's 2 F naught can be available, 3 F naught can be available, 4 F naught, 5 F naught can be available. Sometimes only even harmonics can be possible, or sometimes only odd harmonics can be possible. That means odd harmonics means 1 into F naught, then 3 into F naught, then 5 into F naught, then 7 into F naught. Only even harmonics means 2 into F naught, 4 into F naught, 6 into F naught, like that. Odd harmonics will not be available. Such type of cases will also be there. So you need to see carefully here. Okay. So this is about the pulsating DC signal, and for which rectifier we are going to get this type of output, and for which rectifier we are going to get this type of output, I am going to tell. Okay. Then fluctuating DC signal. Actually, this pulsating DC signal, the output of the rectifier will be given as input to the filter. The filter output is called fluctuating DC signal. So it will be like this. Okay, it is not straight away DC like this. It is not a pulsating DC also. Okay, there are fluctuations in the output of the filter. That's why it is called a fluctuating DC signal. These fluctuations are due to changes in the load, or these fluctuations are due to changes in the supply. Even though if you get the DC, irrespective of the changes in the load and irrespective of the changes in the supply voltage, if you get the pure DC, that is called a regulator. Okay, that is the last stage of the power supply. So power supply is actually involving this rectifier, filter and regulator, so that we can able to convert the pure AC signal into pure DC signal. Okay, so this terminology is required for us to start the rectifiers.